Hi, in this course's first video, we talked about the electromagnetic nature of radio waves and how radio waves at different frequencies behave. In this video, we're going to talk about ways that radio amateurs use radio waves to convey information, be it analog information like a human voice or digital information in the form of characters or even pictures. We do this by modulating the radio wave. There are many definitions of modulation on the internet, but the definition I like best is, in electronics and telecommunications, modulation is the process of varying one or more properties of a radio wave, called the carrier signal, with a modulating signal that typically contains information to be transmitted. In amateur radio, we use many different types of modulation, but the main types are continuous wave or CW, frequency modulation or FM, amplitude modulation or AM, single sideband modulation, SSB, which is a form of amplitude modulation, and frequency shift keying. Continuous wave, or CW for short, is the type of modulation we use when sending Morse code. It is the simplest form of modulation, as we're simply turning the transmitter on and off. Theoretically, the bandwidth or range of frequencies that the signal occupies is zero, but because the CW waveform has a finite rise and fall time, as you can see in this figure, a CW signal will have a bandwidth greater than zero, and CW signals with fast rise times will have a higher bandwidth than CW signals with a slower rise time. From a practical point of view, a CW signal will have a bandwidth on the order of 100 to 200 Hertz. Frequency modulation, or FM, is the type of modulation that most amateurs use once they get their technician class licenses. An FM transmitter actually varies the frequency of the output signal as you talk. This figure shows how this works. As your voice gets louder, the frequency increases. As your voice gets softer, the frequency decreases. For example, if you and a friend were talking on 146.52 MHz, the carrier frequency would be 146.52 MHz, and this is the frequency that you would set your radio to. The modulating signals are your voices. Over the course of a transmission, the actual output frequency will vary above and below the carrier frequency. How much the signal varies is called the bandwidth. The FM signals that we use in amateur radio have a bandwidth between 10 kHz and 15 kHz. 15 kHz is a relatively wide bandwidth, so FM is used mostly on the VHF and UHF bands, where there's plenty of space. The only high-frequency band that FM is allowed on is the 10-meter band. FM receivers demodulate the FM signal by detecting the change in frequency and outputting a voltage proportional to that change in frequency. So the more the signal deviates from the carrier frequency, the higher the output of the detector will be. Another common type of modulation that we use in amateur radio is amplitude modulation. In amplitude modulation, we vary the amplitude of the radio wave, not the frequency of the radio wave. This figure shows what happens when we amplitude modulate a carrier signal. Note that since the amplitude of an AM signal is always changing, the power of the signal is always changing as well. This does not occur with an FM signal. Because you're varying the frequency, the output power of an FM signal never changes. In the process of amplitude modulating a carrier signal, a transmitter also generates two sidebands, an upper sideband and a lower sideband. The frequency of these sideband signals varies as the frequency of the modulating signal varies. So, for example, if you modulate a carrier signal with a frequency of 1 kHz, the frequency of the two sidebands will be the carrier frequency plus 1 kHz and the carrier frequency minus 1 kHz. Amateur radio transmitters limit the maximum audio frequency used to modulate a carrier to 3 kHz, meaning the bandwidth of an AM signal is therefore 6 kHz. It wasn't long after AM became widely used that researchers and amateur radio operators began looking for ways to make AM radio systems more efficient. What they hit upon was single sideband, or SSB. In an AM signal, the information is carried in the sidebands. Not only that, the upper and lower sidebands carry the same information, so they're redundant. That being the case, some smart fellows reasoned that if they could filter out both the carrier portion of the AM signal and one of the sidebands and transmit the other sideband, then you could send that same information with a lower power transmitter and be just as effective. And because you're only transmitting a single sideband, the bandwidth of the SSB signal is half the bandwidth of an AM signal. From a practical point of view, that means you can fit twice as many single sideband signals as AM signals into the same frequency range. While it doesn't matter which sideband you use, it's become common practice to use lower sideband on the 160 meter, 80 meter, and 40 meter bands. On all other amateur radio bands, we use upper sideband. To transmit digital information on the amateur radio bands, hams often use a type of modulation called frequency shift keying, or FSK. Radio teletype, or RTTY, is an example of frequency shift keying. An RTTY signal shifts between two frequencies called the mark frequency and the space frequency. The mark corresponds to a digital 1 and the space to a digital 0, or vice versa. To send radio teletype, a transmitter shifts the transmitted signal between the mark and space frequencies depending on the digital sequence to be sent. There are two ways to do this. The first is to actually shift the carrier frequency. The second is to set the transmitter to single sideband and shift the audio tone modulating the transmitter. When the transmitter is perfectly adjusted so that no carrier or opposite sideband is present in the transmitted signal, the effect is the same as when shifting the carrier frequency. This method is called audio frequency shift keying, or AFSK. While it's possible to use just about any frequency shift, the amateur radio standard is 170 Hz. That is to say, there is a 170 Hz difference between the mark and space frequencies. When using audio frequency shift keying, it's typical to use an audio frequency of 1,445 Hz for the mark frequency and 1,275 Hz for the space frequency. Data is typically transmitted at 45.45 baud on the high-frequency bands. While this is a relatively low baud rate, it does keep the bandwidth down. You can calculate the approximate bandwidth of an FSK signal by doubling the baud rate, then adding the frequency shift. For a 45.45 baud radio teletype signal with a 170 Hz shift, the approximate bandwidth would then be 2 times 45.45 plus 170, or 261 Hz. Now, let's compare the bandwidths of the modulated signals we've just discussed. The signal with the widest bandwidth is an FM signal at 10 to 15 kHz. Even though it has a wide bandwidth, it does offer excellent audio fidelity, And that's one reason it's used extensively on the VHF and UHF bands, where amateurs have a decent amount of bandwidth to play with. Amplitude modulated signals offer good fidelity and a narrower bandwidth, about 6 kHz, than FM signals, and you'll still hear AM on the high frequency bands from time to time. Single sideband is, however, a much better choice for high frequency band operation. Single sideband transmitters are more efficient than amplitude modulated transmitters, and the bandwidth of a single sideband signal is about half that of an amplitude modulated signal. Radio teletype signals that use frequency shift keying are narrower yet, coming in at 260 Hz. You do, however, need a teletype or a computer to operate radio teletype. CW signals are the narrowest of all the signals discussed in this video, with a bandwidth of 100 to 200 Hz. Another advantage of CW operation is that Morse code signals can be easier to hear than voice signals. The disadvantage, of course, is that you must learn how to send and receive Morse code. For more information on modulation types, see these two web pages. Well, that's it for this video. In our next video, we'll talk about how to choose your first radio.